Please give a warm and loud welcome to Dr. John Mather.
Thank you. Thank you. Well, I'm delighted to be here to see you because I have a story to tell you. But I think before I do the story, I should say I didn't win a Nobel Prize. We won a Nobel Prize because anything that I do is done by many, many people together. So I happen to be able to speak for them, but the team that built the Cosmic Background Explorer satellite actually included about 1,500 people, and their names are all in the back of the book. So now I want to tell you the story about the James Webb Space Telescope, but before I get to that, I want to tell you a little bit about who's doing it and why we're doing it. So the project is a joint project of European Space Agency, Canadian Space Agency, and NASA. And so there are thousands of engineers and technicians and scientists working on this. There will be about 10,000 future users of the observatory, because that's all the professional astronomers in the world. And so it's going to be launched in about 2020, early 2020. So I'm the senior project scientist for it. I'm working at NASA Goddard Space Flight Center in Greenbelt, Maryland. So moving on, some of the questions of life. How did we get here? Where did we come from? So I wanted to know this when I was 8 years old, and I still don't have the answer. So anyway, we're working on it. So we know about quantum mechanics. It was found almost a century ago, and it seems to describe everything. It's very mysterious, and if you really want to know how it works, you have to go measure stuff, because the quantum mechanics equations are too hard to solve for almost all cases. So we know the universe is expanding very rapidly now. We know that it started out very young, very smooth, and very hot. It's been cooling off ever since. But we also know that it's unstable. So gravity pulls stuff together as well as organizing everything. So we are here because gravity makes things unstable. So who knew that? So we know the universe is infinite, probably. You can't prove that. And it's very, very old. So that means it's so large and it's so old that it's had time to try out many possibilities, including producing us. So you might think human beings are very unlikely. You might think our location is very special. That's true. But there is at least one of us, and there could be more. So we found out about stored information, how information is transferred through generations of life, through DNA. We found out about evolution. And that was a very controversial thing when it was first recognized by Darwin. And now we can say, maybe it's not just about the survival of the fittest that people used to talk about in those days. We should also say survival of the lucky. So when evolution was first conceived, people thought, well, obviously fitness, that means better in every possible way. So human beings were viewed as the apex of every possibility. Now we know that it was also luck. It's even turned out lately that even the dinosaurs were lucky. They almost perished, but according to the story in Scientific American this month, they were lucky too. So we are here because of that. Engineers have been working on feedback loops, and we know how to design something so it will control a thing to stay the way that you want it. We now are just beginning to recognize that all those information in your DNA is used to run control loops. The decoder ring, the secret decoder ring of your cells that turns that DNA into signals to do something, we don't know how that works yet either. So anyway, lots is to be understood, lots to be known, and if we actually can answer the questions on this page, we will be far in the future. So Lucretius said it before us. He said, no single thing abides, but all things flow. Fragment to fragment clings. The things thus grow until we know and name them. By degrees they melt and are no more the things we know. So even BC people knew about the atomic theory, at least some people did, and it wasn't all so completely mysterious, but people didn't believe them, and it took us a little while to catch up. So how do we know these things in astronomy? Well, we look back in time. Each of us has 2 time machines right here. As you look at things far away, you're looking back in time. Light travels very fast, but it's not infinitely fast, so we can use that. If we could look all the way back to what we call the Big Bang, it was, when I wrote the chart, it was 15 billion years. Now we know it's 13.8 billion. So how do you know how far you're looking? Well, you survey the universe. You draw triangles. Number one, just the way you learn in high school or even grade school. If you move your head from side to side, you see the relative motions of things near and far. You can use that to draw these triangles that it takes to survey the universe. So this works as much as it can out to thousands of light years away. And we're getting better and better at this with observatories called astrometric observatories. There's a new one called Gaia, which is going to give us a totally gigantic catalog of the exact positions and distances of huge numbers of stars. When that doesn't work anymore because they're too far away and you can't draw the triangles, we say, let's use the standard candle method. If I see two things in space and I say, well, I'm pretty sure they're identical, but one of them is fainter, well, it could be there's dirt in the way. It could also be one's farther away. If you can say that it's because it's farther away, then you say, I know how to calculate the relative distances from the inverse square law, so now we can survey the entire universe and look back in time and know how far we're looking. So we also want to know about things moving. The Doppler shift gives us this possibility. So if you spread out the light of a light bulb with a prism, you get a beautiful rainbow. If you spread out the light of a glowing cloud of gas, you get bright lines across the rainbow. If you have a combination of a light bulb and cold gas, you can get what we call spectrum lines, as we see in the stars, with dark marks across the rainbow, and those tell us the chemical composition of those stars. We can also use this to measure the relative motions of things through the Doppler shift. So if we see all the wavelengths of a distant star are stretched, we say it's because it's going away from us at a certain speed. So we can now use this to survey the entire universe and the motions. So back in 1929, Mr. Edwin Hubble drew us a graph. It was the first time we ever knew the universe is expanding and has an age. 1929. So this is the origin of the Big Bang as a story that we think is true. So these little dots on this graph are galaxies, each galaxy being hundreds of billions of stars orbiting a common center. On the vertical direction, he's got the velocity of motion away from us. On the horizontal direction, the speed of the distance that he thought. And so the slope of that line gives the age of the universe. Divide the distance by the time, you get the age. 2 billion years was his number, which was incorrect. So why did he make a mistake? Well, the distant candles that he thought were the same were actually different kinds. Well, too bad, but at least we knew the universe is expanding. It was a huge surprise. Einstein didn't even believe it when he saw it at first, because he knew that couldn't possibly be. Well, he was wrong that time. We found a few mistakes that he made, but relativity, no mistakes. Sorry, we can't go faster than the speed of light. Not that we know of it anyway. So, expanding universe, 1929. We've called it the Big Bang later on, and we'll come back to that because that's a rotten name. So here is the next thing that I worked on. This is the thing that was mentioned in the introduction. This is the equipment that we built at NASA to measure the Big Bang. We measured the spectrum of the heat radiation that's left over from those first moments, and we made a map of the sky. So this actually grew out of a failed experiment that I did for my Ph.D. thesis at Berkeley, and I got to New York at the Goddard NASA laboratory there, thinking I would do something else. But then NASA said, we need proposals for new satellite missions, and my boss said, anybody got any ideas? So I said, okay, my thesis project failed. We should try it in outer space. So we wrote a proposal, just like I told the students to do, and it kept on not losing. So eventually flew 15 years later, and there it is in space. And here are the results. This is the beginning of the data that showed this cosmic radiation has the right spectrum. So these are units that we don't use very much anymore. Anyway, it shows how many waves there are per centimeter on the horizontal direction and how bright the light is in the vertical direction. There's a smooth curve there, which is a theoretical prediction, and the little boxes are right on the curve. And we got a standing ovation when we showed this to the astronomers. So at first I didn't know why it was so important to everybody, but of course there's no answer in the back of the book that says what the right answer is. They like this answer. It means the Big Bang story is true, probably. Eventually the error bars went down to 50 parts per million. So the other second thing that we did was to make a map. So the picture to focus on is the one at the lower right corner, the oval with the pink and blue blobs. That is a map of the temperature variations of the early universe from place to place. So that's the entire sky compressed onto an oval for you. So the upshot is there's small variations apart in 100,000 from place to place. And it's just the right amount to make it possible to explain why we're here. So when Stephen Hawking saw that chart, he said that was the most important scientific discovery of the century, if not of all time. So now I can tell you more why I think that was so important. Number one, those spots explain why we're here. Gravity, acting on the original spots, is able to stop the expansion of the dense regions and pull them back in to make smaller objects like galaxies and stars and eventually planets and people. We're here because of those spots. Thank you, spots. So second thing is, now we know most of those spots come from cosmic dark matter, which we cannot see, but which does have gravity. So it affected the cosmic microwave radiation. So we're here because of the dark matter. Although you don't feel it, nobody has ever seen any of it. We haven't got any particles of it in the laboratory yet. Nevertheless, we know it happened, and we're here because of it. Thank you, dark matter. Third one is, if we could ever figure out what made those spots, we might have a clue about quantum gravity, which is one of those great mysteries of science, and it has not yielded in a long time. We've known since we invented relativity and quantum mechanics that they ought to have a merger, but we can't do it yet. So eventually, when we do, we'll test it on that picture. So that's the beginnings of how we come to be, and I think I have a movie for you coming next, and I don't know if we can turn down the lights enough for you to see it. We'll give it a try. No, maybe not yet. So here's a summary of the story that I tell. The early universe is very hot, very compressed. There is no center that we can find. There is no edge because the universe is infinite. Even the Greeks came across the idea of infinity, and it made them very upset. But that means that the infinite universe is the only kind that can expand into itself. It means there is no first moment. You cannot say the universe sprang into existence because there is no first moment. Time equals zero is not included in the story. Time a little bit after zero is included, but not zero itself. So there is no instant of creation. The universe did not come into existence. It's been here all along. It is not a big firecracker. It is not a big bang like you think of when you hear the words. And there is probably no end. We are not going to run out of time, as far as we can tell. So Hubble Observatory is now 28 years old as of this month, and I'll show you a picture that they just issued to celebrate the fact that it is 28 years old. Of course, it's 28 years old because astronauts have been up 5 times to fix it and improve it, and they have done it beautifully. So I will show you a little bit of what they got and why we're building the new observatory because of them. So here is a picture of the Hubble in the bay of the space shuttle. We had to do this several times. The first time to launch it, then second, third, fourth, and fifth, and sixth times we had to go put it back in the bay of the space shuttle, send the astronauts out to work on it. So, when we launched the Hubble Space Telescope, this is the picture we got, and we were very upset because that's blurry. It's got something in it called spherical aberration because there was a mistake made by the manufacturer of the mirror. And by the way, don't do it like that again. The reason that they made a mistake is they used the same ruler to measure the mirror as they were making it as they did to prove that it was the right mirror. So get 2 rulers. Do not trust that the ruler is the right one. So anyway, we figured out how to fix it, and this is what we got. Wow. The internet crashed that day because everybody had to see the pictures, and they were so much better. So astronomers saw the picture, they started using the observatory. Pretty soon they wrote us a report that said, this is what we want to do next. We want to build 2 things. Number one, we want a big telescope that does infrared astronomy to follow up the discoveries of the Hubble. And number 2, please start developing the technology for studying little planets like Earth around other stars. So we started both. So that's the result of a very poetic report. If you ever want to read a scientific report that is poetic, find that one. It's called HST, which is Hubble Space Telescope and Beyond. So what are the mysteries people want to tackle? Well, how did the universe turn into us? What are the first objects that formed after the Big Bang? Stars, black holes, galaxies? What was there first? We can't tell. We have to go look. Of course, we got a theory, we got a story, but it could be wrong. Has happened before. So how do the galaxies grow? Now our story is the Milky Way and others like it were assembled from thousands of little pieces that were pulled together by gravity. So it might be true, but it's really complicated because after a little while stars blow up. It's all complicated. So Then we know that there's dark matter out there. How does that work? There's the dark energy that we now call the dark energy anyway. It seems to make the universe accelerate. All of that is there. We don't understand either of them. We sort of know how the stars are formed, but only in general terms because it happens in places that we can't see. I'll show you that. We know they do age and they blow up and they die. Even the sun will have an end. Will turn into something else. Exoplanets, well, when we started our project, people did not know that almost all stars have planets. So now we go from how did you possibly get such a rare case as the Earth around the solar system to how come almost every star has planets. And of course now, are they alive? So here's a picture that was taken by the Hubble Space Telescope. It's called the Deep Field. And you'll see lots and lots of galaxies in the picture. And one star. The one star is this little guy over here with the colored spikes sticking out. Those are the diffraction spikes of the spider that holds up the secondary mirror. And the rest of those objects there, they're galaxies. So astronomers were totally surprised by this picture. We did not think this would be true. We did not think there would be so many galaxies. We also did not think that there would be so many little red dots. The little red dots are the ones that are red because the expanding universe has red-shifted the light. It means that we are seeing them as they had just formed, and they're very faint. So astronomers thought, well, we'll build this great telescope. We will see the first galaxies. Well, you couldn't. So that's why they, among other reasons, that was one of the reasons they said, please build us another telescope that's bigger, more sensitive, more powerful, and can see the redder light that is outside the band that the Hubble could pick up. So that's the number one thing from that beautiful picture. Build us another telescope. So here's a beautiful picture that just came out this week because it is the 28th anniversary of getting the Hubble up there in the first time. So picture on the left, that's the visible light picture. Picture on the right is infrared, really different. So the place where stars are being born. And as I was telling you, we can't really see where the stars are being born because we have to look through these glowing clouds and you don't see the stars anyway, the dust is opaque. The right-hand picture shows you infrared view, which is very different. It shows you can begin to see inside the glowing clouds. And this is our hope that we'll be able to use the infrared capabilities of the Webb telescope to see deeply inside and see individual objects being born now. So now a little story about the cosmic dark energy. For many generations, astronomers believed surely gravity is slowing down the expansion of the universe. Well, it's mostly true, but when you go look, you find a surprise. These folks and the teams that they were part of discovered that the opposite is actually true now. The universe is going faster and faster and faster. We say that it's due to the dark energy, which means actually we know nothing about it. We have a name for it, and that's it. What we see actually is the distant stars are fainter by about 20% than they ought to be, which means they appear to be farther away than we thought they would be based on the rate of motion. Okay, big surprise. These folks here in the picture had to check their calculations a lot of times because they did not think this would happen. But it does. In fact, the gentleman in the middle, still working on the problem, is at Johns Hopkins and the Space Telescope Science Institute. He said he was the first guy to go to Stockholm and ask for a stroller for his baby. So young people did this. You can too. So what happens next? Here's the movie that I was telling you about. Can you see it? Yes. This is a simulation in a supercomputer of the gravitation acting on the primordial material to pull it back in to make stars and galaxies. So this is a big box of hypothetical early universe. The computer folks have made it rotate in front of your eyes so you can see the three-dimensional structure as it goes by. Each of those little specks is going to be a galaxy in this simulated universe. And you see that they are pulling together, they come to have a sort of filamentary structure. They're arranged in strings through empty space. And eventually even the strings are arranged into sheets. And you'll see them coming, once in a while you can see edge onto the sheet of material like there. See, everything seems to line up. This was a big surprise. It's not something you would guess, and something the supercomputer can tell you that you would not have thought of. Now, what you're seeing now in the picture is explosions happening in the middles of galaxies. So why does this happen? Well, stars blow up. A big bright star will last about 3 million years, so that's pretty darn quick. Also, something can happen, a black hole can form in the middle of a galaxy, and huge amounts of energy can be liberated as the material falls in, and gravitational energy is released in that process. So this is several billion years into the expansion, 6.7 billion years. This is a very violent time in the history of the formations of galaxies. There are explosions everywhere. Now, as it happens, around 9 billion years into the expansion, the explosions slow down and we don't see them as much anymore. And that's good for us because the solar system is born about that time, 9 billion years after the start. And we're on the outside edge of our galaxy, so we're pretty far away from the explosions that were happening in the middle. We still have a black hole in the middle of our galaxy, but we're far away, and we're lucky. I don't think we would be here if we were close to a black hole. Not because the black hole is bad, but as stuff falls in, it liberates immense amounts of energy that can hurt you. So this is, from my perspective, the most beautiful movie I have ever seen. And why do I think that? Well, this is the universe that we can't watch this happen before our eyes because we only live 100 years, and then we're talking about 13.8 billion. So we need time. We can only do it with a computer and with our imagination to say what really happened. How did we come to be as we are? So, as I was mentioning, teams are required to do all these projects. There's a listing of some of the main people on the team that made that computer simulation. And behind that, of course, is the thousands or millions of engineers that made the computers. Anyway, pictures. Another picture from the Hubble Space Telescope. This is the beautiful Whirlpool Nebula. And the little inset in the lower right corner is the picture that was drawn by Lord Rosse in 1845. It wasn't a Dobsonian telescope. It was a telescope with a 6-foot mirror, metal. You had to climb up a big ladder in order to be able to use it, but he could. So he got that picture and drew that himself. So you could see that with your eye in 1845. Of course, it was dark even in the middle of town in 1845. We've got a different issue now. Anyway, beautiful picture. If the solar system were in this galaxy, it would be way out on the edge, and we would be very far from the middle, protected from bad stuff. And by the way, this other galaxy over here, it's headed in that direction. They are close together. They are going to merge, but we won't personally be here to watch it. It'll take a long time. So another part of our story, this is the Crab Nebula. You think of it as a little white, fuzzy thing in the sky you can just barely see with your telescope. But if you take the Hubble telescope, you can see this amazing debris picture, and X-rays are what makes the blue picture in the middle. This is the expanding remnants of a star that blew up on July the 4th of AD 1054, which we know because the Chinese records can still be read. This is a star you could see in the middle of the day anywhere on Earth. So anyway, part of our story, because this is where the chemical elements of life are liberated back into space to be recycled. So when you look in the mirror in the morning, you are looking at recycled stars like that. And your atoms have been on quite a trip in between being made in the star that blew up and being recycled into you. Amazing. So how do we know these things? Well, we actually have a telescope in South America called the Atacama Large Millimeter Array. It's a collection of computerized radio antennas. And the picture in the upper left here is a picture of a dust cloud orbiting a central star. This is where new planets are being born, so we think. It's thought that the dark rings in between the bright rings are places where new planets are being born, and they're catching and collecting all the dust. So this is a future solar system with roughly 9 planets in it. So it could be sort of like the solar system. Now we have also a story from the computer about our solar system, and this is a story about how the planets might have moved around. When I was a kid, there was a fellow called Velikovsky who said the worlds were in collision. He was crazy. But they do move. Could. This is a simulation by the computer again, of hundreds of millions of years of the particles in the solar system. The little green rocks are the comets and asteroids left over from the formation of the early solar system. And the 4 rings, the colored rings, are the orbits of the 4 big planets, Jupiter, Saturn, Uranus, and Neptune. And it runs along like clockwork for a long time, and then it doesn't. So again, gravitation can make things unstable, and this is the story that seems to match where the craters are on the Moon and Mars and Mercury and Earth. So we can match the story of the craters with a story like this about how after several 100 million years, the rocks out there were compelled to fly everywhere. And this may be the time when the Earth turned from a hot, dry rock into a wet rock with continents and oceans. So this story, which comes from a computer, might be part of our history too. Don't know, but we could find out. Eventually we'll know whether this is right. So, okay, computer, tell me the next thing here. Now I'll get to this more of the story about the Webb telescope. Here it is in its glory. The picture in the upper right shows you a gigantic hexagonal mirror. That mirror is actually much bigger than the picture. It is from floor to ceiling in here. It's 21 feet or 6.5 meters across. The big blue thing here is 5 layers of plastic, metallized plastic, to protect the telescope from the sun. It's a big umbrella. It's as big as a tennis court. So it's from here to the back of the auditorium, would just barely fit. So just imagine your favorite tennis star running back and forth on half of that thing. So the project is, as I mentioned earlier, a joint project of NASA with European and Canadian space agencies. The list tells you the parts they're contributing. The biggest international contribution is the rocket, which is being purchased for us by the European Space Agency. So we will take our payload down to French Guiana in South America when we launch it in 2020. So there it is. I'm not going to tell you the details now about the instruments because we're coming to that later. Here is how the telescope works. There's a big, that big mirror is actually a concave ellipse. Not quite, it's almost parabolic, but not quite. The light is focused onto the secondary mirror there. And that's a convex hyperboloid, and the light bounces back through the whole hole in the snout there, goes back inside. There's a third mirror back in there called a tertiary mirror, which is a concave ellipsoid, refocuses the light again to improve the optical quality of the images. And that combination of things will give us a wide field of view and good image quality for the whole thing. The telescope primary mirror, that big hexagon, is actually made of 18 beryllium hexagons. So why beryllium? It behaves well when you cool it off. Very light, very stiff. And the challenge for us was to make it lightweight. Those mirrors are about 2 millimeters thick, metal, polished very carefully. And the company that does it for us will not tell us how they do it, because that's their trade secret. Anyway, it will operate properly when it's cooled down to about 40 degrees Kelvin, 40 degrees above absolute zero. So how do you do that? Well, you have to make the mirror and polish it up at room temperature, cool it down to the right temperature, see how it warps, warm it back up, polish in the inverse of all those problems, cool it down again and see if it's right, and so that works. So that's how we get it to be the correct shape at low temperature. Here's the list of the instrumentation that we have. There are cameras and spectrometers over the entire wavelength range from 0.6 microns, which is about the red that you can see on this little laser beam, out to 28 microns, which is much, much, much longer, and you couldn't possibly see. Anyway, the cameras and spectrometers are extraordinary in power, lots and lots of megapixels, extraordinary resolution. The pixels are 0.03 arc seconds across, which is even, I think, better than what we have on the Hubble at the moment, but comparable at any rate. Big, not very big field of view. It's similar to what we have on Hubble. This is not the tool to use to survey the entire sky. We've got other equipment for that. So whatever it is you want to study, if you're an astronomer, we've got the tool for you. So we'll come back to, well, we'll talk a little bit about the science later. So this is the steps that it takes to get from the telescope to launch. We start off, we put our telescope together at Goddard Space Flight Center in Maryland with the big golden hexagon and all the instrument packages mounted behind it. We decided we better shake it to see if it'll survive launch. We do this, so there, it is shown there in its big protective plastic tent sitting on top of a shaker, which is able to produce about 50,000 pounds of vibration force up, down, or sideways, and that's scary. It actually caused trouble for a while. We had to figure out what it was doing. It made a buzzing noise that it shouldn't make. So we had to stop and figure that out. But it's okay, we didn't break it. So then we put it in its giant mailbox, and we shipped it around the highway to Andrews Air Force Base in Maryland, and we drove the entire truck, onto the airplane. C-5C aircraft, a very big military transport. Flew it down to Texas, to Houston, drove the truck back out again, put the telescope in the vacuum tank in Texas. I'll show you that in a bit. put it back in the airplane, flew it out to California, and we are about to merge it together with the warm part of the observatory. The rest of the steps, we finish folding it, unfolding it, and verify that it passes tests in California. Then we button it up again, put it in a shipping container again. This is a special barge that will go through the Panama Canal on its way to the launch site in South America. Then we put it on the Ariane 5 launch vehicle, which is a contribution of Europe. And it's a well-tested vehicle. It's coming up at least 75 good launches in a row, and that's really good. Yeah. Then we push the button in early 2020, and then it'll go out into space and become the telescope that it's supposed to be. We have a movie illustrating the process of putting it together at Goddard. This is the big golden hexagon is assembled. The mirrors are assembled onto it. We put it in a chamber to vibrate it, put noise on it. Here they're putting the lid on the shipping container. Technicians are pushing the entire thing out the door. This is the door of the vacuum tank in Texas. There's the super special truck driving down the highway in Texas. By the way, we don't tell anybody till we've actually succeeded in making the trip. We don't want any extra help along the way. And the clearance is about 1 inch between the shipping container and the inside of the aircraft. Here they have to move one of the traffic lights. So this is not the biggest telescope you'd like to have, but this is the biggest one we've got at the moment. So that's getting it to Texas. And I'll show you what we do in Texas. This is the vacuum tank. It's enormous. It was originally built for the Apollo program. We had, of course, to clean it up and cool it down, scrub the sandwich wrappers out, and make it possible to be cooled down. We had to get it to the temperature of outer space, which is really chilly. And anyway, the telescope just barely fits through the door. And then when we're inside, we're able to test it quite well, and we proved that it will do all of its thing in space. This is a test that they could not do for the Hubble. So then we take it out of there. There's the work crew standing around the telescope. You see how little the people are compared to the telescope. What they did, they spent 1.25 years folding up the sunshade and preparing the spacecraft bus, putting everything, all the electronics in it, the rocket engines in it, everything in it, folding it up, making sure it would unfold, and pretending it is in zero gravity with various test equipment, making sure that it'll do its right thing when it's in space. And that part has just now passed through a test chamber where we put sound, noisy sound on it, 150 decibels of sound, which is what it will face when it goes up on top of the rocket. Here's where we're sending it. We're sending it to the Lagrange point 2, this L2 point out here. This is not to scale. This is the sun, the earth, the moon. This is 93 million miles, and this is 1 million miles. So not to scale, but this is a special place. We put it there. The telescope can stay overhead at midnight throughout the entire mission. So it's a good place to go. You can always be in touch with it. And by the way, it was first discovered by Leonhard Euler using the advanced technology of a pencil in 1750. Here is our movie. This shows our scary movie of unfolding the observatory out in space. This whole thing I'm showing you now will take about 2 weeks to do. First, we unfold the solar panels. Then we unfold the little parabolic dish that we use to communicate back to Earth. Now we're unfolding the giant sunshade, that thing as big as a tennis court. Separate the telescope from the warm part of the observatory. It's all done by remote control. There is no astronaut to help it or hurt it. This is a very delicate apparatus. You would actually not like to have an astronaut nearby. And it's got sharp corners, so the astronauts wouldn't like it either. We had to start this design long before there was a serious possibility of having an astronaut go out there. Now we are actually building the rocket and the space capsule that it would take if we needed to go there. But there's nothing in here that was designed for that. Last step here is we unfold the mirrors, and it's not quite ready to go. We have to wait for it to cool down and then focus it. Because that mirror is made out of 18 pieces, and they are all on motors, so they can be twisted, they can be rotated, turned, tilted, and to move back and forth so that they'll all function as one giant, almost perfect mirror. So that's our 14 days of being nervous as compared to terror, as the Mars lander had to do. But of course, the Mars lander had to do it all by himself or herself without human help. We get to help this one along the way by making sure everything works right and then taking the appropriate steps if there's a worry. So we have two of everything. How good is the telescope? Well, it is extremely sensitive. If you were a bumblebee hovering at the distance of the moon, we could see you. Both reflected sunlight and the heat you would emit. So we kind of think something's going to turn up that nobody's ever seen before. So we also, of course, are able to see bright things. You have to really work at it to see Mars because it's so bright, the exposure time has to be really short. But we can do that. So we'll be able to watch Mars, and we'll be able to observe everything from Mars on to the outside of the solar system because we are able to watch moving objects as well as fixed ones. So that'll be interesting. And once in a while, a planet will go in front of its star. We'll be able to study that too. So here is one of our more interesting targets, Europa. You'd say, well, why does the Webb telescope need to look at Europa? And one reason is it's the telescope we will have in 10 or so years when people want to go land on Europa or just fly by. So you may know that Europa is got an ocean under that surface, and that the surface that you're looking at here is actually ice. You see those brown cracks that seems to be places where material is coming up from underneath. And now we have pictures from the Hubble taken with ultraviolet that show water vapor streaming out from those cracks. So that would really be an interesting place to go if you want to hunt for signs of life on Europa. So first thing people want to do is fly a probe through the spouts to see if there's interesting organic molecules coming out. Eventually, let's go land over there. Landing near one of the geysers would be a very interesting place to go. And so we no longer think that we have to melt our way through the ice to get to the bottom to see if something's underneath. So still like to do that sometime. What else would we do? We would certainly like to know if there are planets around other stars that are habitable. So this is an illustration of the clues you would be looking for versus wavelength. So on the short wavelength end, we've got signs of oxygen. So oxygen and ozone, they're of course why we don't get a total sunburn immediately when you go outdoors in the sunshine, because we are protected by the ozone layer overhead. It also means you can't see another planet at those wavelengths from the ground. You also want to look for water, which we have, carbon dioxide, methane, which wouldn't be here if something weren't continually producing it. And so lots of signs of life that you would be hunting for around other stars, on planets around other stars. You want to study what they call the vegetation jump. The Earth has a change of color. At short wavelengths it absorbs, at long wavelengths it reflects because of chlorophyll. So we don't know if other people's chlorophyll is the same color as ours, but you should at least look to see. So a lot of things to find out about planets around other stars, and this is one of the ways to think about them. So how are you going to measure? Well, of course, this is the picture you've probably seen various versions of a lot now. A planet going in front of its own star will make the star blink. Some of the starlight will go through the atmosphere of a planet, if it has an atmosphere, and it'll affect the spectrum that we see. So the planet, the planet will look bigger or smaller at different wavelengths according to the chemistry of the atmosphere. So we'll be able to study that and see what is out there with the Webb telescope. If you tell us, I know a planet is going in front of its star a certain time, a certain hour of a particular day, we'll say, okay, let's point over there, we'll catch it. We'll get that information that you need to know So this has already been a solved problem. We know how to do it. We don't know exactly how well it's going to work, but we will try this. So how special is Earth? Well, pretty special. We'd like to know that, but here we have the right temperature on Earth to have oceans, ice, air, rain, all those kinds of things for liquid water. We have a very lovely, nearly stable, almost circular orbit, so the weather doesn't change all that much through time. We have a very big moon relative to the Earth, which does a lot of things. It gives us tides, it stabilizes the spin axis, and it may be responsible for the fact that we have a very large magnetic field in the center. We have a big iron ball there in the middle of the Earth, but the fact that it spins in the way that it does might be because of the moon. We have just enough water to cover most of the ocean, but not the continents. So if we'd gotten a lot more of those rocks from the sky that brought the water, maybe we just have only ocean. So we wouldn't be here. So we kind of like this one. We have just good amounts of carbon and nitrogen. If there was too much of either of those, maybe we wouldn't be here, or too little, we wouldn't be here. The sun is a pretty good star. It's not all that active. It doesn't have huge flares all the time. It has some. There was one in 1859 or 1856. It was called the Carrington events. It was so bright that the aurora was so bright you could read a newspaper in the middle of the night. So that's interesting because that's a potential catastrophe for modern technology. So we got to think about that one. You could fry the entire electrical grid if bad things happened, and you would not recover for a while. So anyway, we like our star. Other stars like the M stars that are where we can rather easily detect planets, those are probably not good places to be like Earth. So another special thing about the Earth in the solar system is that we have plate tectonics. The continents and oceans are continually being reformed. The continents move around. The oceans are formed and reformed and dissolved, compressed and melted down. So that is changing the biochemistry of our planet as well. And it even may be that that's where life first originated, in those places where the warm water bubbles up out of the bottom of the ocean. So we don't know, but this is a good thing to think about. If we're going to look for life on other planets, we'd like to know, do they have any signs of that? Volcanism. So what are we going to do next? Well, we certainly would say, well, let's have some more telescopes, please. So these are some that are in progress. 3 totally gigantic telescopes. The Giant Magellan Telescope will have 7 dishes each 8 meters across. Immense, and that's already started. The 30-meter telescope will have hexagons made up to 30-meter aperture. Can you imagine 30 meters, about 100 feet across the mirror? And the biggest one in this picture is the European Extremely Large Telescope, the EELT. They've already started that, and in the lower right picture you can see they were flattening the top of the mountain a few years ago. So it's all started, and within about a decade, some of them will be up and running with adaptive optics. So you will have amazing, amazing image quality that even the Webb telescope cannot do. So we will have partnerships. Everybody will say, look what I saw, can I use your equipment? And so we'll have a lot of exciting times for those. So lots will happen. Do not feel that we're running out of science. So what is coming next? Well, the TESS, the Transiting Exoplanet Survey satellite, was just launched by SpaceX. Thank you. You'll hear a talk. It works. As far as we know, it's a fine satellite and will do what it's supposed to do. It will find thousands and thousands and thousands of planets going in front of their little stars out there. The most common stars are the M stars, the little ones, probably not so great for being hosts for life, but there are an awful lot of them. So we'll find them. We will be able to follow up on that catalog of eclipses and transits. The Webb telescope is going up in early 2020. Well, I'm sorry we had a delay because the work is hard. The movie that I couldn't show you actually shows you technicians scurrying around in the clean room in California, and the thing is just an extraordinary challenge to do. Imagine this entire auditorium full of a sunshade that you have to fold up, and you may not make a mistake. So technicians are strapped to diving boards hovering over the equipment to make sure they don't drop anything and that they don't fall. It's rather slow and difficult because they have to be way up in the air above the thing that they're trying to fold up. In about 2020, the astronomers around the country are going to have what I call a science party. We will get together and write a report that says this is what we think the coolest thing is that we should build next. So we're thinking about 4 gigantic telescopes to fly. One would be specifically designed to look for habitable planets around other stars. One general purpose, very large telescope, I'll show you its picture, called Large UV Optical Infrared Telescope. There's a telescope called LINX, which is an X-ray observatory. And there's one called Origin Space Telescope, which is far infrared telescope, and it has to be cooled down to 4 degrees Kelvin, 4 degrees above absolute zero. So all of those are really hard. None of them are impossible. So I'm just not sure how long it'll take. But I think this list is probably going to last for 20, 30, 50 years before we get them all built. So don't feel that you have been left out if you haven't got there yet. If you're a student, you will have a chance to work on these. So in the 2020s, the Europeans are about to launch a sky survey satellite called Euclid. NASA is going to launch a wide field infrared survey telescope, the WFIRST. We are bringing online a gigantic telescope called Large Synoptic Survey Telescope, which will map the entire sky in 3 days. And they're going to tell us 10 million things every night that changed. Can you imagine trying to track down 10 million things that changed every night? And we're even going to have a radio telescope that covers a square kilometer. And the calculation says that is so powerful that if there were an airport radar on a planet around a nearby star, they would know. So pretty shocking what that could do. And I don't think there's going to be anybody out there, but we have to look. So in the very much longer term, there are lots more things coming, but it'll last for a while. We're not running out of science. This is a picture of the large ultraviolet optical infrared surveyor, LUVOIR, and you can't tell how big it is from looking at the picture. But that mirror there could be 15 meters across. So 2.5 times as big as the Webb telescope. And this umbrella, I don't know, 100 meters? I don't know how we're going to do it, but we could do it. I didn't say it was easy. I just say it's not impossible, so we have to work on it. So how far could we go? Well, human beings cannot travel outside the solar system with anything that we've thought of. But we can send robots everywhere, and we already have, to all the planets and some asteroids, dwarf planets like Pluto. Sorry, Pluto, you are a dwarf. You know, by the way, Pluto has more friends than he ever had because we voted him off the island. I was sorry to see him go, but I guess it was the right decision. Computers are getting pretty darn good, and they can beat you at everything that you can play on a game board. Just this week, I read that they can put together an IKEA chair. So that's a pretty big accomplishment. So don't think that they're not catching up. They are. But we're still fragile. We still have to breathe. We don't like cosmic ray damage to our chromosomes. So we're not going very far in the solar system unless we're in a big hurry. If we really need to be in a big hurry, we have to invent fusion drive. And we haven't got it on Earth yet, so it's going to be a long time. But I'd say maybe you could have it in a century. That's not so far off. People that are being born today might see it happen. So not so far off. In the really, really, really long term, well, those robots we're talking about, maybe they will say, hey, you want to go to the nearest star? You want to go visit Alpha Centauri? Let's get together, we'll build ourselves a spaceship, we'll get on the spaceship and wake up after 100,000 years when we get there. The robots also could say, why would I do that? My friends are all home here. It'll be boring, it's a long wait, and by the time I get home, there isn't going to be anybody here. So they might have that discussion. So I'm sorry the things that you see on Star Trek and Star Wars and Space Odyssey, they're not really true. But we have to think about it because there are parts of them that we could make true. So thanks very much, and let's have some, we can now have some questions and answers after this. Thank you.
Hi, I'm Dave Eicher, editor of Astronomy, and I'm here in beautiful sunny California at Celestron, the world's leading manufacturer of telescopes. Today we're going to get the lowdown on a secret, a new hot product that's unlike anything you've ever seen. So let's go inside and check it out. So Corey, Celestron has a really new, exciting, unique telescope. Tell me about the RASA 36.
Yes, the RASA 36, it's a 14-inch RASA. We have had the 11-inch RASA out there for a while now, and we have been secretly developing a RASA 36, a 14-inch version of it. It's still at f2.2, so you will get you very good speed, but with increased aperture.
And this is a really wide field, high-tech camera, astro imaging camera. You could capture incredible wide field views of the Milky Way, big vistas of comets, but there's a really special application that this telescope is perfect for. Talk a little bit about that.
We've been getting feedback from different people. One of them is from a lot of users in the SSA community. SSA stands for Space Situation Awareness. What that means is space junk detecting. More and more satellites are out in orbit, and inevitably they will hit one another, and they become space junk. A lot of them will stay up there for 25 years, and depending on in what orbit they're in, you can be up there forever. What SSA community does is they track these junk so that we can notify the satellite operators so they can maneuver to avoid them. We identify the need, we find a solution. We want to make astronomy fun, and at the same time, we also want to keep everybody safe.
For over a decade, the FIRScope has been one of our customers' favorite products. It's easy to use, affordable, and provides really impressive views for a scope of its size. When the time came to update the FIRScope, I teamed up with renowned lunar imager Robert Reeves to create a telescope that would inspire the next generation of amateur astronomers to explore the moon.
Hello, my name is Robert Reeves. For the past 59 years, the moon has been my passion. Why? Well, the moon is the closest world to Earth. The moon is in our sky almost every night. The moon is close enough that we can see amazing detail on the surface with even modest telescopes.
The Robert Reeves Signature Series FIRScope is more than just a telescope. It's your guide to the moon. The telescope tube is a map of the moon's most notable features so you can learn the moon's geography. This telescope walks you through the basics and unlocks the entire hobby of astronomy, making it fun, easy, and accessible for everyone.
So I invite you to get out under the stars and enjoy a voyage to the moon.